You know, for the longest time, the mantra in AI has been pretty simple. Bigger models, more data, more power. But what if we're starting to hit a wall? What if the real key to smarter AI isn't about just finding more information, but about learning way more from the information we already have?
I mean, seriously, think about it. This isn't some far-off sci-fi question anymore. We are getting really close to a future where we've basically fed AI models most of the high-quality text that exists on the internet. And that creates a huge problem. If you can't add more fuel to the engine, how in the world do you make it more powerful?
And that brings us right to what a lot of researchers are now calling the data-bound era. The whole game is changing. See, for a long time, the biggest limitation was just raw computing power. But now, the real bottleneck is high-quality, unique data.
We've got these incredibly powerful computers, and they just keep getting better. But the well of pristine data is starting to run dry. That old strategy of just scraping more and more of the web, well, it's hitting a point of diminishing returns. And that forces us to ask a totally new question. Which kind of AI model can squeeze the most intelligence out of every single piece of data it sees?
So this problem sets the stage for a really fascinating showdown between two completely different philosophies of AI learning. In one corner, you've got the reigning champion, the architecture that powers most of the large language models you use and hear about every day. And in the other corner, a powerful challenger with a totally different game plan.
So on the left, we've got our champion, Autoregressive models, or AR models for short. Think of the whole GPT family. And on the right, the challenger, Diffusion Language Models, or DLMs. Let's dig into how these two actually work.
Autoregressive models are actually pretty intuitive. They read text just like we do, from left to right, and their entire job is to predict the very next word in a sentence. That's it. It's a super efficient process that has turned out to be unbelievably effective when you scale it up.
But then you have diffusion models, and they are wired completely differently. They don't go word by word. Instead, they take a piece of text, mess it up on purpose by hiding a bunch of words, and then their job is to learn how to reconstruct the original. They learn to denoise the text, looking at the entire context from every direction at once to fill in those blanks.
Okay, now this is where things get really interesting. What happens when you pit these two approaches against each other in this new data-scarce world? Well, the research uncovered this phenomenon they call the intelligence crossover.
And here's the headline, the big takeaway. When you force both of these models to learn from the exact same limited data set over and over and over again, the diffusion model, our challenger, eventually overtakes the autoregressive champion.
And this right here illustrates the champion's weakness perfectly. Just look at this graph of an AR model's performance. It learns really fast at the beginning, but after just a few passes, what researchers call epochs over the same data, its performance just flatlines. It gets saturated. It literally can't squeeze any more knowledge out of the text. Now let's look at the challenger. This is the diffusion model on the exact same data, and whoa, the difference is just stunning. Even after hundreds of repetitions, its performance just keeps on climbing. It's like a super data learner, constantly finding new patterns and signals where the AR model saw absolutely nothing left to learn. This is that crossover, right here in action. Just look at how that accuracy keeps going up even after hundreds of passes.
And get this isn't some one-off fluke. It is a predictable trend. The bigger the AR model is, the more quickly it just memorizes the limited data, and the earlier this intelligence crossover happens. The champion's greatest strength, its massive size, actually becomes a liability in a data-constrained fight.
So that begs the obvious question, right? What is going on under the hood? How is the diffusion model able to pull this off? Well, it really comes down to three key advantages. You could almost call them secret weapons.
Let's break down these secret weapons that give diffusion models such a powerful edge.
First up, any order modeling. Unlike AR models, which are stuck on that rigid left-to-right track, DLMs can learn patterns in any direction, forward, backward, inside out. Second, super dense compute. DLMs are absolute workaholics. They spend a vastly larger amount of computational energy on every single example they see. And third, built-in augmentation. That whole process of masking and denoising naturally creates millions of little mini-puzzles from each sentence, giving the model so much more to learn from.
And when we say more compute, we're not talking about a small increase.
I mean, to reach their full potential on just one piece of data, diffusion models can spend over 100 times more computational power than an AR model. They don't just read the book, they analyze every single word, sentence, and paragraph to death.
This chart right here really shows that trade-off visually. It measures the cost in something called flops. You can just think of it as a raw measure of computing horsepower. To squeeze every last drop of intelligence out of the data, DLMs are willing to pay a massive computational price during training. It's kind of a brute force approach to getting a really deep understanding.
So, what does this all mean for the future? It really suggests a fundamental shift in how we might think about designing and training the next generation of AI.
At the end of the day, it all boils down to a trade-off. It's a strategic bet on the future. Autoregressive models are data-hungry but pretty efficient with their compute. Diffusion models are the exact opposite. They're compute-hungry but incredibly data-efficient. They are placing a bet that in the future, compute is going to be cheaper than new, high-quality data.
And the researchers themselves put it perfectly. If unique data really is the new gold, then diffusion models offer a powerful way to mine every last ounce of it, even if it means using a bigger, more expensive drill.
All right, so let's recap. What's the final scorecard here? Well, when data is limited, the challenger, the diffusion model, can absolutely beat today's champion. This intelligence crossover isn't a fluke, it's a reliable phenomenon, and it's driven by their unique ability to model text in any order, use that superdense compute, and basically create their own training examples. And all this points to a future where data efficiency could become the most important metric of them all.
Which leaves us with one final, big thought to chew on. As we start to hit the absolute limits of the information we can feed our machines, maybe the next great breakthrough in AI won't come from finding more things for them to learn, but from discovering fundamentally smarter ways to learn in the first place.